So that's what the theoretical variance of our estimators are. But of course, we don't actually know what sigma squared is. So to estimate this variance, we need to estimate sigma squared. So let's start talking about standard errors, or the square root of our estimated variance. So remember, the variance is sigma squared over SSTJ, that total variation in xj, and then 1 minus this r squared, which is kind of capturing this correlation. But again, we can't estimate this variance because of this. Maybe I'll be more clear here. This is the variance of beta hat j. But it's not the estimator. We can't use this yet because we don't know what this number or this variable is. So we're going to have to estimate it. Well, we're not going to know what it is, right? We have to estimate it. So let's talk about standard errors. And so we know that sigma squared is the expectation of u squared, just like in simple regression, because the mean of u we're assuming is 0. This is the variance of our u. And we know that 1 over n times the sum of ui squared is an unbiased estimator of sigma squared, but we don't know what ui is. We don't actually observe the ui's. I'm just going to switch colors here so this light green doesn't look the greatest anymore. We don't know what these ui's are. We don't observe them. But we do have something that looks like the ui's. We have those estimates, just like in simple regression. We have the residuals. So maybe we can use those. Our residuals as an estimate of ui. And then we're going to go back to what we talked about with simple regression. I guess I'm just kind of explaining this again. Where now our estimate of sigma hat squared is going to be all of these ui hat squared added up over n minus k minus 1. We talked about that last time. This is the degrees of freedom correction. It's kind of accounting for the fact that we're using some of the information in our data set when we're estimating these betas. So we're just making sure we're getting a consistent estimator of sigma squared with this regression or this expression, which is just another way of saying this is SSR over n minus k minus 1. So again, this is those degrees of freedom that you've seen before. So you can think of it as n minus k minus 1 or n minus k plus 1. And this is the number of parameters. So the idea here would be that, we have our sample size minus the number of parameters is our degrees of freedom correction. Okay, so I'm going to erase all this, and what this is going to give us an expectation is the true value. So it's going to be an unbiased estimator of sigma squared. So just kind of continuing on with our discussion of standard error, what I was saying was our sigma hat squared, in expectation is going to be the true sigma squared, this true variance of our error term. So it's an unbiased estimator of sigma squared, that SSR over n minus k. Remember that sigma hat squared is SSR over n minus k minus 1 from that last form. We're just saying in expectation we get the right thing, right? Just like those properties we want in an estimator, this is an estimator for sigma squared. It has this nice property we want. And so our standard error of beta hat j, which is going to be really key for hypothesis testing about one parameter, is going to be equal to the square root of the variance, so just sigma hat rather than sigma squared hat. Got rid of the squared and we took the square root, over SSTJ, we're going to put this all in brackets, 1 minus r squared j to the 1/2. So we're taking the square root of the denominator of our variance formula as well. So this is the formula for the standard error. And again, the same things that affected the variance are affecting the standard error. So the variation in xj is affecting this. The larger the variation, the lower the standard error. The correlation between xj and the other variables is affecting our standard error. The greater the correlation, the greater the standard error. And one final note, we're not going to prove it, but Gauss-Markov theorem. So under assumptions, 1 to 5. So remember, linear in parameters, random sampling, no perfect multicollinearity, expectation of u given all the x's equals 0, and that fifth one that we added was homoscedastic errors, the fact that the variance was constant for all levels of x. If these assumptions hold, then our estimators are blue. They're the best linear, unbiased estimators. So by best, it means it has the lowest possible variance. So they have the lowest variance of all the estimators we can come up with. It's linear because it's linear in parameters. It's unbiased because the expectation of the beta hat j's are the true values and their estimators. Under these assumptions, assuming that's true, which are pretty strong assumptions, right? But this means our OLS estimators are pretty good if this holds. So what we're going to start doing in the next module, the next chapter, is hypothesis testing. And then we're going to think about having kind of loosening maybe some of these assumptions as we go, and then introducing different types of variables.